All right, so here we have a disk D. It's a disk because x squared plus y squared equals to 1 will be a circle, the unit circle, right? But if you let it less or equal to, then it contains everything inside the circle. Then what I'm trying to do is I'm going to take this region, the unit circle, and send it to, by this transformation, and it will be some unknown shape, be something else. And then my question is, what is the area of this thing? So let's try to see what's going on. Now, first of all, I do know that the image, which is S, will contain the origin, because if you plug in 0, 0, this gives you 0, right? So 0 goes to 0, 0 goes to 0. So it's inside some domain. So we can, for a moment, forget the fact that this is an inequality. Just take the defining equation and see what happens if points that satisfy this equation, meaning points on the boundary of the circle, is sent to under this map. Okay? And the way we do it is, let's just define that the boundary of this equation is satisfied by capital X and capital Y, where these are the images of small x and small y under this transformation T. So in other words, I'm going to say that this is x and that's y. Is that okay? All right. So we have x, capital X equal to 2x plus y, capital Y equals to x minus 2y. Now, with just this, I have no idea what the shape looks like. I would really need an equation between x and y. The problem is we have no idea what the relationship between x and y are, right? So you somehow have to use the relationship between small x and small y to get the relationship between capital X and capital Y. Right? And let me show you how that's done. Just multiply 2 to the second one, so this is 4. Subtract, and that gives you x minus 2y equals to y plus 4y, which is equal to 5y, right? So we see that small y is same as x minus 2y over 5. Okay? What about small x then? We could have not multiplied by 2, but instead we could have multiplied 2 to this one, right? And then we could have added them instead. If we do that, then 2x plus capital Y would be, these two will cancel and you get 5x, so that you get x equals to 2x plus capital Y over 5. Right. Now the reason I do this is because I actually know the relationship between small x and small y. What's the relationship between small x and small y? It's this one, x squared plus y squared is 1, right? So what I can do is I can take those things and plug it in here. And let's see what that gives us. This is capital X minus 2, no. X is 2x plus capital Y over 5 squared plus capital X minus 2 capital Y over 5 squared. Okay? And then that's equal to 1. Everyone okay with this? Now, what did we just achieve? We figured out a relationship between capital X and capital Y. This still looks cryptic, but it's not too bad if you simplify it. So let's do this. See, if you square top and bottom, the bottom will be 25, right? So I'm going to multiply by 25 both sides so that you get 2 capital X plus y squared plus capital X minus 2 capital Y squared equals to 25. And then I expand this. This would be 2x squared, 4x squared, capital Y squared, but then there's double the product, right? So you multiply this with this times 2, it would be 4xy. And then plus, this will be capital X squared minus, actually plus 4y squared minus 4xy equals to 25. And then these two cancel. You have 5x squared plus 5y squared equals to 25. So x squared plus y squared would be 5. Right? Is that okay? Now, a question. What is the geometric object described by this equation? It's a circle of radius, square root of 5. Right? Square root of 5 squared. Okay? So we know that this mysterious thing was really square. So here, the original domain D was 1, and this new S is square root of 5. This one. Okay? But we're not there yet because it didn't ask for what S is, it asks for the area of S. So can you tell me what the area of S is? How do you calculate the area of a circle? Pi r squared. So the area,
which is pi times 5.
Pi r squared, which is pi times
square root of 5 squared.
Yep.
Which is just 5.
Which is 5. Okay, that's the answer. It's a purely geometrical question. Area is 5 pi. Now, this question doesn't seem to have much relationship with linear algebra because other than the fact that this is a linear transformation, right? I said generic linear transformation from a plane to plane should look like ax plus by and cx plus dy. Right? But someone who remembers our last lecture would actually know a shortcut to getting this answer 5 pi without doing all this. I wonder if anyone remembers. So you can say that this is solution 1. Solution 2. What's a simpler solution? Does anyone know?
Use the determinant.
Determinant, okay. So let's think about the determinant of t. What's the determinant of t? 2, 1, 1, negative 2, right? What's the geometric meaning of the determinant?
It's a small circle when you're making it.
Yeah, but when you have a transformation, what information does the determinant tell you? The multiplier of the change in the area. Right? That's what it does. Okay? So, since the determinant of the matrix form of T is what? AD minus BC, right? It's 2 times negative 2 minus 1 times 1, which is negative 5. Oh, I wanted to make it positive 5, but I beat it. Negative 5. But it's okay. What I didn't tell you was that if the determinant is negative, it flips the orientation. So if you have a right-handed, if you have 2 vectors, it could be either right-handed or left-handed, right? If you have vector u and vector v, and if this angle is less than 180 degrees, then you would say that uv is right-handed, whereas vu would be left-handed. uv is like going counterclockwise, and vu would be going just clockwise. Okay, so if it's plus, then the linear transformation takes a vector configuration that's right-handed to right-handed. If it's negative, it will flip it. Right? So that's all it does. But when you talk about the area doesn't care about negatives, right? So you just take the absolute value of this. So what's the area of D? This is a circle of radius 1. This, so what is it? Pi 1 squared, which is pi, right? So area of S would be pi times the absolute value of -5, so that's 5 pi. Done. Okay. Same answer as before, without much calculation, right? That's, yes?
So do you always have to do the absolute value?
Yeah, because we're talking about area. The minus part tells you the orientation. The absolute value part tells you the ratio between the original shape, the area of the original shape to the area of the shape.
So whenever you're using the determinant, you use the absolute value to calculate the area too?
Yeah, if you want that, yes, yes. Any other questions? All right. Now, let me just add a little bit more. Suppose you have vector AC and then BD. Then you can think of this parallelogram, right? And you can ask, what's the area of this? Let's say you want to know this area. Okay? So again, the question is, if you're given two vectors in the plane, and if you use those vectors to form a parallelogram, this third point will be simply the sum of these two, right? The coordinates are like a plus b, comma, c plus d, right? So that gives you a parallelogram. And let's say you want to know the area. How do you find the area? Well, think of the following transformation. A, B, C, D. And this transformation takes 1, 0 to where? Where does it land? Do the matrix multiplication. What do you get? A and then C. Right? So 1, 0 goes to AC. How about A, B, C, D? 0, 1. B and D, right? Okay. Now, think about the shape that these two vectors give you. See, this one is 1, comma 0. This one is 0, comma 1, right? And then the parallelogram made by these two vectors is actually a square. What's this area? What's the area of the square? Huh? What?
1.
1, 1. It's 1 times 1, right? Okay. So what's the area of this one then?
It's going to be different.
There's a transformation that takes this to that, right? What's that? I just showed you. This is the one, right? So what's this area?
So just 1.
No. We just learned something about transformations. You will change the area, right?
It does. I change it.
Area, but it changes the area by what?
It's a determinant.
The determinant, right. So what's the area of this? It's 1 times
The determinant.
determinant of A, this one, which is AD minus BC. The absolute. That's what it does. Now, this is something that you learned in Calculus 3, except that nobody told you what's happening. Even me, when I told, I think, who took Calc 3 from me? Is there anyone who? Oh, really? Okay. So, I didn't even explain this because we didn't have enough language. I couldn't explain the transformations. We didn't have the time. But it's like this. In 3D, you can think of A, B, C, D, E, F, G, H, I, this matrix, right, as a transformation that takes the cube, size 1, right, to these column vectors. Right? So it's going to be transformed to another 3 vectors, right? And the transformation of this cube under this image will be, what shape would that be? Do you remember the name of that thing? It's a 3-dimensional object where every sides are parallelograms. What is that called? Every face of this 3-dimensional box-looking thing is a parallelogram.
Cylinder?
No.
Cube.
No, not cubed.
Paralleloid?
No, parallel pipe.
Piping, yes.
Yeah, that's what. Parallel pipe. So that's the word. Okay. So if I say this transformation is T, then under this operation T, you end up with some parallel pipe thing where every pipe has 3 other parallel pipes. Okay? Every edge has 3 other parallel things. Okay? So that's called parallel pipe. And the volume of this object is given by what? The determinant of these 3 things. Right? So if you take the determinant of this, I haven't introduced the determinant formula for this one in this class, but you learned it in Calc 3, right? You know how to do that row expansion or some other things, right? Yeah. So this determinant, and if you take the absolute value of this quantity, it gives you the volume of this parallel pipe. Because if you think about it, what's happening is that the volume transforms, and the ratio between the volume is given by the absolute value of the determinant. And then when you have three vectors, again, there's the right-handed or left-handed. Right? If it's positive, then right-handedness will be preserved. If it's negative, then right-handed will turn to negative, left-handed, or vice versa. Okay? So if this determinant is positive, we call the transformation orientation preserving. If it's negative, then we say the transformation is orientation reversing. Oh, and then, by the way, we actually learned something else here too. We learned that this is actually given by the triple product of 3 things, right? It's like U dot V cross W, where you can either view it as U, V, W as these 3 column vectors, or you can use row vectors. Either way, it's the same thing. So that's where you learn this in multivariable calculus. But what I'm trying to say is that there's a geometrical meaning to determinants. It tells you how the area transforms, how the volume transforms, how the I don't know, okay, four-dimensional volume. There are volumes for every dimension, right? So you can have like higher dimensional volume. All these will transform under this determinant. Oh, and then there's one more thing I want to say. What do we know when... This is something that we learned in Calc 3 as well. If you calculate this triple determinant, we got 0. What do we know about these three vectors? Hmm?
Any orthogonal?
Not orthogonal. Calc 3 was so long ago, right? You guys were maybe a year or two. Okay. Yes?
Is it reversible?
No, it was like, but you actually have the geometry intuition now. You're actually in a better state to understand this. What happens if this is 0 in terms of geometry?
You have no volume.
You have no volume. What does that mean? They're all in the same plane. So that means, this means that these column vectors, or even the row vectors, are coplanar. Coplanar. They're in the same plane. It means that one of the vectors can be written as a linear combination of the other two. You can take this one and represent as something times this one plus something times this one. Because one vector lies in the plane generated by these two other planes, two other vectors. That's what it means. So that's another thing that you learned in Calc 3 without really getting much explanation why, but now you kind of understand that.